For the next assignment, so to recap what we did last week, would you mind? Okay, thank you. This is Bate. He's with us again. So last time we wrote a parser for very simple expressions that can be either integers or if expressions, and we wrote that as a recursive descent parser, also known as a top-down parser. And the data structure that we generated from the parser looks like, what was my header file called? .h, compiler.h, interesting. So this is the data structure that we use for the expression. So the expression has a type. The type can be either integer or if. And in case if it's an integer, it gets its value, which is just an integer. And if it's an if, it has three sub-expressions that are the condition and the consequent and the alternative. And our task for today is to write an interpreter for these expressions. And the way that the semantics work is that an integer evaluates to itself, like 1, 2, 3 becomes 1, 2, 3. And an if expression needs to evaluate its condition. And if the condition is 0, then the result is the evaluation of the alternative. And if it's not 0, then it's the result of evaluating the consequent, meaning that essentially 0 is false and anything else other than 0 is true. And as I said in the in last week's call, the way we're going to do this is by writing a recursive evaluation function. And I give the prototype here. So I'm going to make start by making an interpreter.c file. I'm going to include the compiler.h. And this is the function that we're implementing. So what do we do?
If this expression is of type, the type or exp or arrow is an integer, so exp arrow.
Right, so I'm actually going to write a switch on the type. So I'm going to write switch type. So if it is an expert integer, then what do we do?
Return, well, you have to cast it as a
no, I don't actually have to cast.
Oh yeah, you could just do I.
p.i. Yeah, I have it in this union thing here, which is weird for people who don't know C. And even if you do know C, it might still be weird. Essentially, a union, this is just an aside into details of C. Essentially, union means that each of these members of the union occupy the same space in the union. So the union is as big as the biggest element, and you basically have to know which one it is. Otherwise, you'll probably get garbage. Although you can also use it to, for example, surreptitiously cast one thing into another. So you might, one element of your union might be a struct that contains 4 bytes, and then the other element might be a 32-bit integer. And so you can use, you could write something into the 32-bit integer part of the union and then access the bytes of that 32-bit integer individually. We don't want to do that. We just use it to save memory. Basically, we know which kind it is, and we just hope that we're not making a mistake. Otherwise, we'll get garbage pointer values or garbage integers. And if it's an if, what do we do?
Then we do if expr of v if expr dot or arrow
No.
condition.
Yeah, if expr dot condition.
Is it? I think you need an arrow on that, right?
No, I do not need an arrow.
What? Okay, I just okay. That if that dot
Right,
or
so,
you have to eval expr
right.
of that thing, then
So basically, I could say if this is not equal 0, but in C that's implicit because you actually use integer Boolean values. So C kind of works the same like simpling in that case. So if that is true, then
basically return the eval of the of the consequent.
Right. So this is almost else return eval expr of expr b if expr dot alternative. So this is it almost looks like the definition of if you discount all of that weird dot and pointer stuff, it almost looks like the definition of what the interpreter should do, and that's the implementation. So it's really very simple. And everything else, default, we're gonna just assert again. Assert include assert.h, assert false, and there we go. I wonder whether, yes, I have actually included all of that here. So now we can just write the driver. Maybe we should have written the driver before, but it doesn't really matter much in this case. So we're gonna, in this case, have I'm gonna call it eval main, static void eval main, takes a context, and what it does is first it parses an expression, and then instead of printing the expression, it will eval the expression in 64T result equals eval expr of that expression, and that we're going to print f. And there's this stupid thing here. Our result. And that's it. Think it's going to work?
What's that PR stuff?
Oh, that's for properly printing a 64-bit integer.
Okay.
It essentially evaluates to a not evaluate. It's a macro that expands to a print format specifier that's the correct format specifier on your architecture, on your system for a 64-bit integer. Yeah. All right, let's try that out.
And like there's nothing in between that thing and the new line. Macro and
there is nothing between
macro. And
oh no, it's because this evaluates to a string, and in C there's a thing called string concatenation that the preprocessor does. So if you write something like ABC123, then the preprocessor out of that makes ABC123. However, data argument not used by format string. What does that mean? Oh, it's because I forgot the percent. Yes, that's what I actually need. Use functions can, yeah, that's fine. Okay, so let's try that out with, well, I actually have a few test cases, so I could just go to here and say tests, test, I don't know what it's called now. It's called interpreter 1.3. So tests, test, this thing here, that's the subdirectory, and my interpreter is in here. And 4 tests, 0 failures. So if you look at the tests, tests interpreter. For example, there is if false.sl. Ugh. I haven't turned that off. But I could run it on this one. And I can see that it evaluates to 2 because 0 is false, so it's the else thing. Of course, the simple case is just an integer. Which, that's the integer. So yeah, there's one nested one. Let's look at the nested one. If nested SL. So that's the one from that I talked about last week. The assignment. This one, which should evaluate to 3, because this one here evaluates to 0, which means that we need the else branch here, and this one evaluates to true. So we get this. And if we run it, I've already established that it works, but here we go. All right. On to the next assignment. So in this one, we're back to the parser. And this time we're going to add unary and binary operators to the expressions. So unary operators are operators that just take one argument, and those are not and negate or minus, arithmetic negation. And those come before the expression. So, for example, just -5 is the arithmetic, the negative of 5. So this is the minus is the operator, and 5 is its argument. And the other case is a parenthesized binary expression. And the reason why we're always parenthesizing the expressions is so that we don't have to handle operator precedence yet, because that's maybe the trickiest part of our parser, but we're going to do that later on. So in our case, these always have to be in parentheses. So if you want to write, let's say, 1 plus 2 times 3, you can't write that. Instead, what you have to write, these have to be parenthesized, and then this has to be parenthesized. Because otherwise, the parser would have to know that the multiplication has a stronger precedence than the addition. And again, we're doing that later. So if you look at the grammar is really just as unambiguous as the last one. So if you look at the first token when parsing an expression in your recursive descent parser, you'll see that it's either an integer, in which case the expression, because no other kind of expression can also start with an integer, or it will be an if token, or it will be one of the unary operators, so either this one or that one, or it will be an open paren. And then once you know which kind it is, you can just continue parsing. And here, for example, in the unary operator, you would go, oh, I have a not, so I'm going to parse an expression now. And the only thing that's not super trivial is, in this case, you don't know yet which binary operator you're getting, but the binary operator is, again, just one token. So that will determine which kind of expression it is. And I'm going to write I'm going to extend my data structure so that you kind of get an idea of what the syntax tree should or could look like. We're going to have, and here, this is another case of, there's different ways to do this. So for example, I could have one type of unary operator expression, and then the unary operator expression could, for example, unary could contain, I could actually put the token type in here, right? So I could, because I'm lazy, I'm going to put the token type T. I'm going to put the operator in here. Not super clean, but yeah, whatever. The other way you could do is you could just do away with the token type and make the expression itself either a not or expr negate, right? In which case, when you're interpreting or when you're just printing the thing, you would have to do one switch less. Like you wouldn't have to also switch on the token. But I'm going to be lazy here, and it doesn't mean that you should be. Make up your. Both are totally fine. You're not going to lose out on anything later. So it's going to be unary or binary, and the unary has a sub-expression, which I'm going to call operand. And I'm going to have binary one. So this is for binary. So this will also be just the token type of the binary operator. And this one has two operands, namely a left and a right. And then the thing that you need to write is, after you've parsed it, you again need to make it output this thing so that you can then run it through the test suite, which I am going to extend with a few tests for these kinds of expressions. Does that make sense?
Mm-hmm.
Did you have any difficulty with that? Anything that, okay. All right, so the take says it's easy.
I guess there's one idea from the scanner that you may want to use for the binary operators, but I don't want to spoil the thinking process.
Okay. I'm not quite sure what you're referring to, but where are you typing? Well, I've talked about look ahead in the last in last week's call, but I don't think you need look ahead here. Why do you think we need?
Well, I guess the way I implemented, I think I used look ahead. I gotta check this out again.
One reason we're going to need look ahead later is to determine when expression is finished, right? So if an expression can be, for example, any sequence of A plus B plus C plus D plus whatever, and at some point it could end with either end or close paren, and we don't want to consume that because the parser that's calling us one step further up wants to actually consume that token. In that case, we need to look ahead. But here, we always know when an expression is going to end before we even see that token. So I don't think we need to look ahead.
Not necessarily, but just,
what
because
is that?
might have a binary operator here. Then you might have to.
Oh yeah, no. That was just what I was talking about. We're not far yet.
But still within the parentheses.
No, but there can only be one expression and one operator and another expression. And if there's a nested sub-expression in there, then it has to be parenthesized in and of itself.
Oh,
right? You can never have A plus B plus or 1 plus 2 plus 3.
Okay.
You can't have that. You can have open paren, 1 plus open paren, 2 plus 3, close paren, close paren. All right, no look ahead needed yet. So then, there we are. until next time, which is Monday. Cheers.